Okay. Now let's talk about the conduction of electrons. Okay. We have now EK diagram, right? We know that electron, if I put into the crystal, its energy and its wave vector are related to the EK diagrams, right? What is the implication of this thing? What do I want to achieve from this? Eventually, we want to know the conduction properties of the material. If I have a solid, I would want to know what is its conductivity. How does it behave if I apply some voltage across it? Does it give me a good amount of current? Does it give me no current? Does it give me a medium type of current, right? As like in a semiconductor, right? So all of those material properties, all of those electrical properties are depending upon the material properties. The EK diagram is a material property. For different material, you will get different EK diagrams. Okay. Now, how do I represent my electron inside a crystal? We know that it's an eigenfunction. It's a Bloch wave function, but that's the solution. That's just the solution of time-independent Schrodinger equation. Just an eigenfunction. So several states. But is that the only possible solution of the Schrodinger equation? Remember, we have just solved the time-independent Schrodinger equation. What about the time-dependent Schrodinger equation, which is the actual Schrodinger equation, by the way? What did we do? In simple problems, we first found out time-independent Schrodinger equation solutions, which are energy eigenfunctions. Then we multiplied them with e to the power minus iota et over h bar to give it some time dependence. And then we multiply them with some constant coefficient, sum those up, and then we said, oh, the general solution is going to be some linear combination of these all particular solutions, right? That's what we did. Okay. In case of a free particle, what did that give us? In case of a free particle is a plane wave. If you solve the Schrodinger equation with V equal to 0, you will get e to the power iota kx. But is that the possible solution? No, it's not the possible solution. The general solution is linear combination. And general solution comes out to be a wave packet. So a particle which moves in a free space, that is best represented by a combination of plane waves. That's a wave packet. A wave packet is localized in some region of space, right? Say from x1 to x2. The probability density of the wave packet is high. In other regions, it's almost 0, right? So it's a packet, but it does not have a definite position as well as definite momentum. No definite momentum, no definite position. In fact, no definite energy also. Okay. So that's a picture of free particle. Similarly, in the semi-classical description of an electron in a crystal, we can form a wave packet. The most general solution of electron moving inside a crystal will be a wave packet. So what are my particular solutions? Particular solutions are the Bloch wave functions. So Bloch wave functions are eigenstates. But you have not yet linearly combined these eigenstates and saw what the general solution will be. So the general solution is going to be a wave packet. So let's see. So what do we have? We have the solutions of the time dependent Schrodinger equation for a crystal potential will be of this form. So first we find the particular solutions of the Schrodinger equation. So that will be your Bloch wave function times e to the power minus iota et over h bar. Now for different values of k, we have different eigenfunctions. That's why I am denoting it as a k, index k. So it will depend on k. For different values of k, you will get different wave functions. So there has to be a k here, right? K1, K2, K3, K4. So you will get different wave functions, different Bloch waves, right? Because psi of x is equals to u of x into e to the power iota kx. So change the k, you get a different wave function. Okay, and this energy corresponding to that energy eigenvalue is Ek. Okay. So the most general solution is going to be again a linear combination of this, something like this, where Ck is a constant and you have to sum this up over all possible values of k. Yeah, all possible values of k. What are all possible values of k? They can be usually contained in one Brillouin zone, because outside that it just repeats, so you don't need that. So when I am summing up this k, I can simply take k from minus pi by a to pi by a. Okay, I can contain my all possible values of k, all unique Bloch wave functions I will get only within one Brillouin zone. After that it will just be a repetition, so you don't need to add that thing again, right? Okay, so this k is over one zone. Okay, now because these k values are very closely spaced, the spacing is 2 pi by capital L. Capital L is the dimension of the crystal. So 2 pi by L will be a small number because L is large. So what will happen? So this summation can be converted into integration because k values are very closely spaced, right? So the summation will become almost continuous and will become integration. So when we have an integration, so what will happen? So this ck is going to become a function of k. It's the coefficient itself is a function of k, phi of k, and then you have this psi k as it is, right? And e to the power minus et over h bar, and of course you are integrating with respect to the k. Okay, that's what you get. Of course I have written it from minus infinity to infinity, but you can contain it within one Brillouin zone, minus pi by a to pi by a. You can do that. Okay, now what is my psi k? Psi k has to be a Bloch wave function. So if it's a Bloch wave function, what will be the form of the Bloch wave function? So psi k is going to be equal to some uk x, u of x, which is a periodic function of x, into e to the power iota kx, and that combined with this will give you e to the power iota kx minus ekt over h bar, right? So that's what you get. So this is a general solution. Now this has different wave vectors, right? It also has some kind of a time dependence. So if you compare this thing, if you remember the free particle case, we had something very similar here. Okay, we just did not, I mean in the free particle we did not have this u, otherwise everything was same. How do I form a wave packet, by the way? To form a wave packet, what did I tell you? I told you that this phi of k, this phi k, it has to be non-zero only in a small region of k. Okay, it will peak at some k equal to k naught. If I have phi of k peaking at some k equal to k naught, then I explained it to you, I described it that this is going to look like a wave packet which travels with some velocity, which we call as a group velocity. In that case, I can linearize my relation between E and K. If K is contained within very small region, I mean this phi k is non-zero within very small region, then I can linearize this E as a function of K. Okay, approximately. And then that gave me the concept of group velocity, that there is a wave packet which travels with some velocity. What was the group velocity? D omega by dk. Omega was h bar into E divided by h bar, right? Okay, so I would suggest you to go back and just revise those concepts. So what I did was this. So phi of k, it's a non-zero only within a small region around some k equal to k naught. So that's the center value. Whenever we have something like this, we will get a wave packet. Why I am saying that? Look at it closely. This is nothing but the Fourier transform. It is some kind of a Fourier transform. Okay. Now what happens in the Fourier transform? Whenever you try to contain the information in the say frequency space, you get some spread in the real space, right? The say the x space, right? In this we have k space and the x space, the position space, which will also look like this. If I plot psi is a function of x, so it will be something like this, right? So it has some kind of a center position x0, so this is x1, this is x2. You have some spread here and you have some spread. You narrow it, so this will be spreading more. You narrow this, so this will be spreading more. Okay. So it's a similar, but it's a semi-classical. So this is called semi-classical description of the electron in the crystal, right? Because we are seeing the electron as a wave packet, and we saw in case of free particle, the wave packet kind of follows Newton's laws. So whatever, say if I have, what is Newton's law? Force is equals to mass times acceleration. The acceleration is d2x over dt square, where x is position. But in case of a classical particle, that position is very well defined. Now in case of a wave packet, we told that, yeah, it follows the Newton's law, but you'll have to replace the position with something else. What was that something else? Some kind of an expectation value or the mean value or the center of the wave packet. Okay, so that x will be replaced by the center of the wave packet, x0. So x0 moves, the center of the wave packet moves, and it follows the Newton's law. Similarly, in a crystal, when we describe the electron, why I'm saying it's a semi-classical. Semi-classical means it has some classical physics, some quantum, right? So the quantum wave packet nature is coming from the quantum, but it still follows the Newton's law, that's classical. So it's a semi-classical description. Okay, so let's have a 10-minute break. So electron in a crystal is in the form of a wave packet. Okay, it forms a similar law to Newton's law. Why I'm saying similar will become clear. So, okay. Okay, so for a wave packet, we can define its velocity, right? So wave packet moves with a group velocity. So we can similarly define the group velocity of a wave packet inside a crystal. What we have is this. So Vg is d omega by dk, and where? At k equal to k naught, where that phi k peaks. So the center of that. So that. Okay, and what is my omega? Omega is basically E is equals to h bar omega. So it's simply E by h bar. So dE over dk. So this is an important relationship, right? So it means that Vg is equals to 1 by h bar dE over dk. Now depending upon what is the relation between E and k, you can have different group velocity, right? So E versus k, where is that information contained? In the Ek diagram. In the Ek diagram, you have all of that information. So depending upon different Ek diagrams for different materials, you can get different Vgs. Even for the same material, for different values of k, you will get different Vg. Okay? Even for different bands, for the same material, you will get different Vg. Because E versus k relationship is in the form of several energy bands. So say you are in the first band, your Vg is going to look like something. For the second band, the relationship between E and k might be slightly different, right? In fact, it can be very different, right? So you will have a different Vg because you have a different relationship in the different bands. Okay. So now Vg is related to the mean value of the position of the wave packet. Wave packet does not have a definite position, but what we can say, we can calculate the expectation value or the mean value of the wave packet, or we can say the center of the wave packet that is moving. When the wave packet moves, you can just focus on its center and it moves. And so something like this. So if you have a wave packet like this, so you have x naught somewhere here. So this is the center of the wave packet, and when you have a velocity, group velocity, so this is moving, this whole thing with Vg. So you can relate this Vg with this x naught, which is the expectation value or the mean value or the center of the wave packet, right? So how do you relate them? So what is the relationship between the velocity and the position? So v is equals to dx by dt. Similarly, for this case you have d by dt of expectation value of the position, because there is no definite position, is equals to vg. So as you have some velocity, if you have some finite group velocity, so your position will change with time, right? Because the wave packet is moving. And how does it change? It will depend upon what is the relationship between E and K. Okay? So movement of electron inside the crystal will depend upon the relationship between E and K, and it will be different for different bands. Okay. Now, similar to the free particle case, I told you that our wave packet in the crystal, the electron wave packet in the crystal, will also follow some kind of a Newton's law, right? So this velocity exists even when you don't have any external force acting on the crystal. This will still be there. Okay, because you don't have dE by dk equal to 0 everywhere. You may have dE by dk equal to 0 at some places, but not everywhere, right? So the relationship is something like this. If you plot in the, say, reduced zone scheme, what do you have? You have something like this. Yeah? So what is dE by dk? So this is energy. This is k. What is dE by dk? The slope of E versus K, multiply with 1 by h bar, right? So the slope is 0 here, but slope is not 0 here. So there is some finite slope here, right? So even when I don't have any externally applied force, electron is still moving with some group velocity, some finite group velocity, and it remains constant. It doesn't change with time. It doesn't change with time because the relationship between E and K is not changing with time. So over time you have the same group velocity. If you haven't applied any force, the group velocity stays the same. So what if I apply an external force now? My particle, the wave packet particle, will follow some kind of a Newton's law. I know that. What about the crystal? So electron inside the crystal will also follow some kind of a Newton's law. So in the crystal, say F is an external force. Now this force is an external force. It means the force other than the crystal forces. By the way, why the Vg was non-zero? We didn't talk about that. Why the group velocity was non-zero even when you don't have an externally applied force? Because there are crystal forces, right? Of course, electron is inside a crystal. So there are forces of interaction between the crystal and the electron, right? And due to the Schrodinger equation and all, right, it gives you a wave packet solution which is moving inside the crystal. Okay, but when I apply an external force, say F, which is in addition to the crystal forces, so then that force is what? Rate of change of momentum. In the case of a free particle, classical particle, say if I have, so dP by dt gives me force, rate of change of momentum, right? And in case of a free particle wave packet, I take the expectation value of the momentum. So this. Something like this. So F is equals to D expectation value of the momentum by t. But it is the expectation value of the particle wave packet. In the case of a crystal, we don't take the expectation value of the momentum, but what we take is crystal momentum or EC. So this is what holds for a crystal. So now this is the importance of the crystal momentum. Okay, so what is the crystal momentum? H bar k. Remember I told you in the last class, H bar k, it's not an eigenvalue of the momentum, actual momentum. No, it's not an eigenvalue of the actual momentum. So this does not represent an actual momentum. This is called crystal momentum. H bar k is crystal momentum. We calculated the eigenfunctions, right? Remember e to the Bloch wave functions. So Bloch wave functions are ux into e to the power iota kx. So Bloch wave functions are not the eigenfunctions of the momentum also. So if they are not eigenfunctions of the momentum, this does not represent the eigenvalue. But h bar k is called something else, which we denoted as crystal momentum, PC. Okay, so it's an extension of the concept of the momentum to the crystals, especially because this relationship holds for the crystals. Okay, but F, remember, F is external force and PC is crystal momentum here, not the real momentum of the particle. Okay. Now what will happen? What will happen? If I have, say, constant external force, say if I have an electric field, right? So this force will be some charge times the electric field. Say if it's an electron, so then it will be minus q times E. E is the electric field. So say this is a constant. What will happen to k? dk by dt is equals to some constant. It means k is going to vary with time. If k changes with time, according to equation number 3, now k, Vg I have is dE by dk. So it's a function of k, the group velocity, right? It's the slope of E versus k. If my k changes, dE by dk will also change. So then my velocity will change. And of course my position will also change. So indirectly, right? So force changes my k changes the group velocity. Okay, so it's like that. Okay. Okay, so let's try to establish a relationship between. Now I know that when I apply the force, it changes my velocity through k. Force changes the k changes the velocity, group velocity. Now let's try to establish a relationship between the group velocity and the force. Now for a classical particle, we know that what's the relationship? What is the relationship between the velocity and the force for a classical particle? For a classical particle, force is equals to mass times acceleration. What is acceleration? G by d. So this is the relationship. If I have a force, my velocity will change in time. Can we establish a similar kind of relationship for an electron moving inside a crystal? Can we do that? So you have all of these equations. Can you try to establish a relationship like this? What should we do? I have force that changes the k, and k Vg is related to k through this. What should I do? Okay, let's see. So let's try to see what is the rate of change of group velocity. Okay, so what is dVg by dt? dVg by dt, I can write it as dVg by dk into dk by dt. Yes? What is dk by dt? It's related to force. It is force divided by h bar. Force is equals to d by dt of h bar k. So dk by dt I can calculate, right? It's force. What is the relationship between Vg and k? So this is d by dk and Vg is my 1 by h bar into de by dk. What do I get? So this derivative and derivative becomes double derivative. So 1 by h bar square, this h and this h becomes h bar square, and you get d2e by dk square times the force. Okay. Now dVg by dt is equals to something into force, or we can write force is equals to dVg by dt divided by this factor. Yeah, force is equals to dVg by dt divided by this factor. So this will become 1 divided by this thing. That 1 divided by this whole thing, let me call that as some m star. Okay, so what is m star? M star is equals to 1 over 1 by h bar square d2e by dk square. This is called effective mass of the electron. Okay, so now I have an electron wave packet, and there is a relationship between the dVg by dt and the force, but m is not the actual mass of the electron, it is effective mass. F is equals to m star into dVg by dt. This is effective mass, not the actual mass of the electron. Actual mass is simply m, right? That m is not appearing anywhere. What we get is a mass that depends upon the band structure. See, d2e by dk square, this is going to come from the band structure. Different materials will have different electron effective masses. In fact, again, for the same material in the different bands, you will get different effective mass, because this E versus K relationship for the same material in different bands will be different. Yeah, so it means m star will be different for different bands. Even for different values of K, you can get different values of m star. So, because E is a function of K, d2e by dk square, it still might be a function of K, right? It may not be exactly constant. Yeah, so you have F is equals to m star into dVg by dt. So some things you need to notice. First of all, this force on the left hand side is an external force. It's not the total force. It's not crystal plus external. It is just the external force. And on the right hand side, what I get is dVg by dt and m star. So where is the impact of the crystal force then? That is all contained in the effective mass. So where is this coming from? Crystal. This is all the impact of the crystal forces, d2e by dk square. Okay. Yeah. So the impact of the crystal is contained in the effective mass, and that is related to the external force. Force is equals to m star into dVg by dt. So it's as if, see, if I have an electron moving inside a crystal, I can still use Newton's law, I can still use its particle picture, but the impact of the crystal, to account for that, I'll have to replace my mass with the effective mass. That's the deal. So you can replace the whole crystal thing with a free particle thing, not a free particle, I mean you can replace the whole crystal structure or the information of the crystal, right, with a classical particle, but you'll have to replace the mass with the effective mass, plus you'll have to replace the velocity with the group velocity of the wave packet. Okay, yeah, so this is some kind of force in force is equals to mass times acceleration. Acceleration is dVg by dt. Okay. Now this has several implications. You will see that it's a very weird crystal movement of the electron in crystal is very different from a free particle, a classical particle moving in for example under the application of a force. It's a different relationship. I mean, although the form of the equation is still the Newton's law, but you will see that because of the crystal, the presence of the crystal, there will be several things that do not hold for a classical particle, that do not hold true for a classical particle. For a classical particle, if you apply the force in a particular direction, it will keep accelerating. Its velocity will keep increasing. We will see that that will not be the case for a quantum particle or a particle which lies in a crystal. Okay, so before that, let's talk more about the effective mass. So we have the effective mass as this. So what is this thing? What is the, if I have a function f, right? It's a function of say x, f of x. Y is equals to f of x. What does this thing give me? d2y by dx. What does this thing give me? Double derivative, what does the double derivative denote? It denotes the curvature of the y. Okay, if you have two sharp curvatures, this will increase. If you have less curvature, this will decrease. Okay, so let me show you. So say, so this is m star is proportional to the inverse curvature of the E versus K. Okay, so say I have E versus K, I have these two cases, right? And say I'm talking about calculating the effective mass at K equal to 0. Which one will have a higher effective mass? Can you tell me? I have two band A and B. Which one will have higher effective mass at K equal to 0? So whose curvature is larger? So this is more curved, right? This will have a larger value of d2e by dk square. So if the denominator is larger, m star will be smaller. Larger the curvature, smaller the effective mass. Similarly, this is more flatter. So it has smaller value of d2e by dk square. Okay, mathematically d2e by dk square tells you how curved the EK diagram is. So we have near K equal to 0, my MA star will be greater than MP star because this is smaller, this is larger in the denominator, right? So there is an inverse relationship. So M star A is greater than M star B. Okay. So different materials can have different EK diagrams, and that's why they will have different effective masses. Or again, for the same material even, you can have different bands and you can have different effective masses. Yeah. Okay. Now let's take one more example. So say my E versus K looks like this. Right? I have just drawn one branch of EK. Remember in the extended zone scheme we had branches like this. Right? So say E versus K looks like this. Okay. Now what do I need? d2e by dk square. So let me first differentiate it one time, right? So what will be my dE by dk? So near, so this band is, if I draw it more properly, is going to be something like this. In a reduced zone scheme it will be something like this, right? So near the bottom and the top, what do I have? What is dE by dk? 0. So slope is flat, and somewhere in the middle the slope is maximum, right? So it starts from 0 and becomes maximum and then again becomes 0. dE by dk, the slope. Okay. So the dE by dk will be something like this. So somewhere in the middle it is peaking, and here the slope is 0, the slope is 0. Slope of the tangent to the curve, if I draw, so the slope is 0 here and slope is maximum somewhere in between, dE by dk. What will be the plot of d2e by dk square, by the way? So you differentiate this curve one more time. So what will be the d2e by dk square? You take the slope here, which is, by the way, this slope is positive or negative? Positive, right? This is a positive slope. What about this? So you will have a tangent like this. So this will be a negative slope, right? Theta greater than 90 degree, negative slope. Theta less than 90 degree, positive slope. Okay. And what will be the slope here? 0. So positive slope, positive value of d2e by dk square, 0 value of d2e by dk square, negative value of d2e by dk square. So what will be the relationship? It will look like something like this. So it starts from some positive value, becomes 0 and then becomes negative. Yeah? And this is a perfectly valid band. We calculated it. Now for a perfectly valid band, you see that d2e by dk square can be positive as well as negative. What does it mean? Effective mass can be positive as well as negative. You can have a negative mass as well. Okay? So effective mass can be negative. Real mass is never negative. effective mass can be negative because it's coming from the band structure relationship, but that can be negative, d2e by dk square, right? Okay, what will be the implication of that? It will become clear in a moment. Okay, so d2e by dk square, if I have a bottom, so near the bottom, if I see near the bottom of the band where the curvature, so the curvature is upward here, right? So it's curving upward. You see, whenever I have an ek which is curving upward, I have a positive m star because d2e by dk square will be positive in that part. Whenever I have a region where my ek is curving downward, so it's curving downward, right? So then d2e by dk square is negative. So my m star is positive near the bottom and negative near the top. It's always the case. So near the bottom you will have a positive effective mass, near the top you will have negative effective mass. Okay. Now let's talk about this parabolic approximation in ek. Now we have seen that the relationship between E and K can be quite complicated. Yeah, even for a simple case, Kronig-Penney model, it came out to be really complicated relationship. In practice, what we do, we try to approximate the ek relationship in the regions that are important to us, and we usually replace that relationship with a parabolic approximation. What do I mean by that is, say you have bands like this. Okay, so you have this band and the next band is this, the band next to that would have been like this, but let's focus our attention on these two. So say this is the valence band and this is the conduction band. Now, usually what happens, my carriers that can carry current, they usually lie near the bottom or the top of the band. So these regions are very important for us. The bottom and top of any band is very important because usually carriers try to accumulate there. Why they do that? We'll see that later. Okay, so what we do, we try to replace the relationship between E and K around these regions with some simple approximations, and that's what the parabolic approximation is. So you see that this is some kind of a parabola, right? If I limit my K to very small region, so you see it's like curved parabola. Okay, I could have fitted it with some more complicated expressions as well, but the simplest thing I can see is that it's some kind of a parabolic relationship, but only near the bottom. If I go farther from the bottom, the parabolic approximation that deviates, right? So this is the parabolic approximation, and if I am close to K equal to 0 here, so that relationship is matching with this black line which is the actual band, but as I go higher in K, it is deviating. So near the band edges, so this is the band edge, right? We denote this band edge by EC because it's the band edge of it is the bottom of the conduction band, and this is the top of the valence band denoted by EV. So this is the energy axis. Okay, and similarly here the parabolic relationship holds only near K equal to 0. Now it may not be K equal to 0 always, it can be some K equal to K naught also, but what I am trying to say is that the parabolic relationship holds good near the bottom or the top of the band, near the edges. Okay, so what we do, say the edge is at K equal to K naught. In our case it is K equal to 0, but it could have been that this is here but this is displaced somewhere here. It could have been. In fact, in silicon that's what the case is. So in silicon you will get valence band here, but the conduction band will not be at K equal to 0, it will be somewhere here. Okay, so at K equal to some K naught. So near the band edges, I can make this parabolic approximation, and let's say that K is equals to K naught in general. So what do I have is E is approximated as some constant E at K naught plus some constant into K minus K naught square. So this is my parabolic relationship, right? Anything which is a function of say square, right? F as a function of x f is equals to say some constant into x square. So that's parabola. It's a perfect parabola. This thing is a displaced parabola, displaced by k naught. So what is the say I have this. You remember y is equals to some kx square. That's my perfect parabola, right? K is a constant, not the k of the wave vector k. It's just a constant. Say some cx square. Now I want to displace this thing, right? Because I told you that my conduction band for the silicon can be somewhere here, right? So in general, what if I want to just displace it? So what will I do? To displace a function, I replace x by some x naught, x minus x naught, right? So this will be x minus x naught square into c. And in this, y is equals to 0 at x equal to 0. Say I also want to displace in this direction. So I want this parabola say somewhere here. Okay. So in general, I have a parabola somewhere here, which is displaced in x and displaced in y. So that parabola will be y minus y naught equal to c into x minus x naught square. What is y naught? Y naught is the value of y at x equal to x naught. You put x equal to x naught, what do you get? Y equal to y naught. So this is exactly what that is. Just replace this y by e. So e is equals to, so what is this? Y is equals to y naught plus c into x minus x naught square. So y is my e, y naught is e calculated at k naught, c is that constant, x is my k minus k naught square. Okay. So this is my parabolic approximation. And if you take the double differentiation of this, so what will happen? What will happen if you take the double derivative of this? So this becomes 0, constant into 2k minus k naught, that is the first derivative. If you differentiate it second times, what do you get? You will get d2e by dk square equal to constant. It means near the band edges, d2e by dk square is approximately constant. So my effective mass near the band edges is approximately constant, and these are the regions which are most important for us. So these are the regions where carriers try to accumulate. So you can associate a unique effective mass with them, a constant effective mass. Otherwise, in general, it changes with k, but near the bands, it is constant, and that's the region which is most important to me. Okay. So that's why I can assign a constant effective mass. So that's why in books, if you look at the electron effective mass, they will give you a single value. They will not say m as a function of k. I mean, of course, you can calculate it from the band structure, but usually they will assign it a single value. Why single value? Because I'm talking about an electron which is at the bottom of the conduction band. Okay, which is the region important for me. And at the bottom, my effective mass remains almost constant because that parabolic relationship, parabolic approximation holds there. Away from it, parabolic approximation does not hold. Okay. So the last topic I am going to cover will take 5-10 minutes. What if I apply now? So what do I want? Eventually I want to apply some kind of an electric field across the crystal and get some current. Yeah, that's okay, EK diagram, effective mass, that's all fine. But what happens when I apply some voltage? What kind of current do I get? That's the most important thing for me. But before we go into the details of that, I would just want to give you an example. What is the implication of electron being a wave packet moving inside the crystal with a group velocity which depends on the band structure? What are its actual implications? That will become very clear with this. So say I have a crystal and I apply a DC voltage across it. Now if I apply a DC voltage across a crystal, what will it do? It will create a constant macroscopic electric field. So that F external, the external force, is going to be simply now, what will be the value of that? Charge times electric field. Okay, if I apply a constant voltage, DC voltage, that creates some constant electric field, and the force is going to become charge into electric field. So let's do that. So say if I have a DC voltage applied, so force is equals to minus q into xi. I wrote it by xi letter, electric field, because it might be confusing with the energy, that's also E. So let me call electric field as this xi, and of course if you have an electric field, if you have a force, it's going to change my wave vector. How it changes the wave vector? By this equation, right? H bar into dk by dt is equals to minus q times xi. So wave packet, the wave vector of the wave packet changes as a function of electric field. Okay, now which k I am talking about? The center k. The wave packet had several k, but I am talking about that k naught, about which the wave packet is centered, right? So that it is that k naught actually. Okay, now my k is going to change. Of course, what will happen is going to evolve with time. So say this electric field is constant, because I have a DC bias, of course it will be a constant. So I can simply integrate this equation. What will I get? If I have a function whose differentiation is a constant, it means that function is linear. So what do I get? I get this linear relationship between k and time. You can integrate it both sides from 0 to some time t at t equal to 0. So you can do that. So kt will be equal to k at time t equal to 0 minus q into electric field by h bar into t. So it's a linear function of the time. If you apply the electric field, k is going to linearly change. Now assume, say my xi is in the negative direction. So then this negative will become positive. Okay. So what will happen? Q is the electronic charge, by the way. So k will increase with time. If I apply a negative direction electric field, my k is going to increase with time in the positive direction. Okay. Now I know that my k is also going to change the group velocity, because Vg is equals to 1 by h bar into dE by dk. K changes, my velocity will change, because Vg is a function of k. Yes. So how does it change? So Vg is equals to dE by dk. K changes, Vg will change. Let's look at it. Let's look at an actual E versus k diagram, and let's try to plot my velocity. So it will look like this. So I'm now drawing my Ek in the repeated zone scheme. So I have a periodic band. So this is the first Brillouin zone, but let me extend it to the second also, right? In general, it's going to be periodic. I'm just focusing on, say, some band, right? One of the bands. I had several such bands, but let me focus on, say, one band. Okay, so I have an E versus k which looks like this, a periodic function of k. And what will be the velocity? You take the differentiation, dE by dk. So what is dE by dk here? 0. dE by dk here, 0. dE by dk here, again 0. Okay, what is dE by dk here? So it starts from 0 and the slope is negative here. So it has a negative peak, the velocity. So this is velocity, right? Goes back to 0 because the slope is 0 here. Again, it starts from 0, the slope is 0 here, slope is 0 here, but slope in somewhere in the middle is maximum. So it will give you maximum Vg, and it is positive. So it is positive Vg. So velocity can be negative, positive. Again, it's a repeating, so it's negative, positive, something like that. Now say I have an electron which at t equal to 0 is situated here at k equal to 0. Okay. At time t equal to 0, the wave vector of the electron was 0, let's assume. And now I switch on my electric field, I apply the DC bias, and my k starts to increase through this equation. If my k starts to increase, what will happen to the velocity? It will increase, reaches a maximum, and then it starts to decrease. Is it possible for a free particle? Is it possible for a classical particle, by the way? I apply a force on the particle, a constant force, it will always accelerate. Its Vg will always keep increasing, will never decrease. Right? It will just pick up that force and will keep moving with a faster and faster velocity. Acceleration is constant, so velocity will keep increasing. But in the case of a particle inside the crystal, velocity increases up to a point, up to a particular k, and then it starts to decrease. So this is an interesting thing which is unique to the crystal. Why this is happening? Because other than the applied force, you also have the crystal forces. So it's the combination of the external force plus crystal forces that is deciding how my Vg is going to be. Okay? So that crystal is important. You can't simply replace a particle inside a crystal with classical particle because of the presence of the crystal forces, which go into the Schrodinger equation and decide the wave mechanics of the particle moving inside the crystal. Okay, so you have Vg becomes maximum, decreases, and interesting thing is it also becomes negative. What is the physical implication of that? See, you have a particle, it's moving fast, and then it slows down, and then velocity becomes negative. The negative velocity means it changes the direction also. So it becomes like this. It starts to return. Okay, it never happens in a classical case. So what happens? It goes negative, becomes maximum in the negative direction, and then it starts to slowly it starts to slow down again. Magnitude of the velocity becomes closer and closer to 0. It becomes 0 again here, and then again velocity becomes positive. So it started like this, returned, increased the velocity, slowed down, again return. What is it doing? Oscillations. If you apply a constant force to a crystal, it is supposed to oscillate the wave packet. These are called Bloch oscillations. Okay, these are called Bloch oscillations. In reality, it doesn't happen. In an ideal crystal, theoretically I showed you the electron has to oscillate. But in reality, you never hear anything like this. Have you heard of this thing before? You might never have heard this before because it's not even important. Why? It means that if I apply a DC bias and electron is oscillating, I am getting an AC current. With the DC, do you get AC? Do you get alternating current with the DC? You never get that. Why? So whatever picture I showed you, that is for a perfect periodic crystal. Perfect. Are real crystals perfect? They are far from perfect. So there will be some imperfections in the crystals. Okay, there will be some impurity, there will be some defect. That is going to change your crystal potential. So if you have some periodic crystal potential and suddenly you have a defect, so you will see that there is some bump in the potential. Bump in the potential energy. And what will that bump do? So if you have this, a defect, so you have a crystal and then you get this bump suddenly. So this is a defect. Okay, what will this do? This disturbs the periodicity. Now, say my velocity, say my wave packet is picking up, the k, and the velocity is increasing, and suddenly this wave packet encounters this. What will this do? It's just going to scatter it. The wave packet will bump into it and get scattered. Some of it will, go beyond this as well. So as you apply the force, the wave packet picks up a small value of k. If you keep applying the force, if it was an ideal crystal, the k might have been, changing with time unlimitedly, right? It will just change with time. But here, it changes with time. You pick up some k, and before you even reach, say somewhere here or even here, you get bumped, you get scattered, right? So say somewhere here, so you picked up this much value of the k, and this got scattered. And then as soon as it gets scattered, so you again kind of reach k equal to 0. You electron transferred all of its energy, say, to the scatterer. Okay, although that's not always the case, but let's assume. So it picked up some velocity, and then it got scattered. Okay, and it again reached the Vg equal to 0. Then it again picks up, and before it k increases. So this behavior, to see this behavior of oscillation, you have to cover this much of k. Only then you will be able to see the behavior, right? You have to cover this zone. The width of the k must be equal to the zone to see the Bloch oscillation. But before we reach this k, say in this region, the electron gets bumped here, scattered, right? So we'll never see this spectacle. Okay, that's why we are going to be limited somewhere in this region, always, because my k is never going to become a k which is comparable to the zone width. K is going to be much smaller than the zone width in reality, always somewhere here, right? So you will never see these Bloch oscillations unless there have been, I think, some experiments which have tried to show this. I think they have been successful also, but in reality, especially for the semiconductors, no, you don't see this. Okay, practically. Yeah, if you create a semiconductor, which is perfect, doesn't have any defect, and by the way, if the crystal does not even have any defect, even then you will not see it. If you put that at the room temperature, what will happen? The atoms will start to oscillate. So that will create perturbation in the crystal potential. So you have this perfect crystal potential when the atoms are stationary. So whatever I have talked till now, it's actually the picture at temperature equal to 0 Kelvin. Okay, at non-zero Kelvin, at some finite temperature, you don't have this perfect crystal. So you have the crystal potential plus the perturbation potential. Where is that perturbation coming from? By the movement of atoms because of the thermal energy. It's like an addition to the crystal potential. So if you have some V, add some delta V to it, and that delta V is coming from the oscillations. Okay, so again, because of the oscillations of due to the thermal energy of the atom, my wave packet is coming, may get scattered. Okay, so in reality, you will hardly see this.